Hello everyone, I'm your host Raghu Veera Raghavan, and in this session we will be showing you how to perform lightning risk assessment using ETAP software. The outline of this presentation is to understand what is a lightning risk assessment, what are all the standards that are associated with it, and the lightning flash density around the world, across the globe, and how it is updated real time and on a yearly basis, and the statistical data, and also the available lightning risk assessment calculation methods to determine whether a surge protection device or a SPM is involved or not based on the analysis performed. We will also be demonstrating all these features into our software tool, and we will be able to open up for questions and answers once it is done. Well, the picture in the background clearly tells you that the lightning strike has a good relationship with electricity. Well, thanks to Benjamin Franklin and his kite experiment, I like his work, plus also the fact that he's on the $100 bill. The experiment was done on 1752 in Philadelphia. Well, it makes sense to me now on another dimension as to why the TV series It Is Always Sunny in Philadelphia is a good sitcom to give us a sense of humor, because this experiment was performed by Franklin on a rainy day in Philadelphia, which contradicts to the title of the TV series. Well, a lightning risk on a particular facility needs to be assessed properly to save human life and avoid property damage. The evaluation of the risk of lightning strike on or near the structure under consideration is important, because most of the power surges are caused by lightning strikes, and it is very nonlinear on the season due to inadvertent weather conditions. Risk assessments performed to recommended lightning protection system, that is the outcome of it, and the risk management for the protection of life and property while considering the continuity of operation and system reliability is the key to why the lightning risk assessment plays a vital role in continuity of service, at the same time the protection of human personnel and the actual property. Well, what is the need for the LRA? We do have number of surges, power surges that causes over voltages and causing a lot of power outage and also damage to the equipment and personal human life. And also we need to have a proper risk assessment in order to prevent damage and fires, and also account for unpredictable weather patterns regardless of the foreseeable weather forecast that we have, and also to improve the asset protection such as telecom stations, power lines, and other environmental influences that is associated to a structure. The most common available standards, the National Fire Protection Agency, the NFPA 780, which is the standard for the installation of lightning protection systems, and the international standard IEC 62305-2, the 2010 version. So these two standards talk about the requirement and the process of getting to lightning risk assessment, and the IEC standard also mentions how to perform the surge protection system to be installed based on the assessment performed initially. Here, the stroke density map that is provided could be based on different factors. Some of them may be related to the lightning directly hitting the structure before it hits the ground, or sometimes directly from the sky to the ground itself. In either cases, the evaluation of the lightning flash density and the corresponding the area around that particular affected structure is important to evaluate. Similar to Africa, we do have Europe that also has several flash densities per square kilometer per year. And as you can see, the number of flashes ranges between from 2 to almost like 8 or even sometimes 12 flashes per square kilometer per year. And these statistical data prove that there is a lot of assessment required to be done on every structure that is involving people, that involves environmental factors, and also the proper protection of the actual facility and the equipments associated with it. In the United States, we do have several locations, mostly in the East Coast, and also be able to check between 12 and up flashes per square kilometer per year. There are many methods available to get the statistical data, and a lot of real-time websites that could provide us an accurate details on the most recent occurring events. And there are many ways to assess this in terms of the structure of the equipment and in terms of the actual roof type and the corresponding the construction of the equipment itself. So the lightning risk assessment calculation methods are basically calculated based on the equivalent collection area, which is mentioned in the NFPA 780 and the IEC 62305. A simple formula for a rectangular structure that is available could be calculated based on its length, width, and the height of the structure, and the equivalent collection area of a rectangular structure that is simple with the length L, width W, and height H is none other than the area defined by the intersection between the ground surface and a straight line with 1/3 slope which passes from the upper parts of the structure, touching it there and rotating around it. A good illustration is shown in this building right here. The equivalent area, looking from the top view or the aerial view, could be easily calculated based on the above formula for a simple structure or rectangular structure, and none other than calculating the equivalent intersection of that height and width in the area defined and the ground surface and a straight line with a 1/3 of the slope that evaluates it. So obviously it originates from the intersection of the height and the width, and it passes from the upper parts of the structure, and it's going to be spread around the rotating area of it. We do have other structures if it is considered to be for a prominent part that encompasses all portions of the lower part, can also be evaluated using equations provided by the NFPA 780, and the determination of the equivalent area, the collection area, will be used to determine whether a lightning risk assessment is present or not. If we have complex structures, or this is available in Annexure L of the standard, where a prominent part encompasses all portions of the lower part basically. So different equations are developed to actually get the correct geometry of the area, of the equivalent collection area, and it could be basically categorized into two simple geometry. The structure of the complexity is based on a simple regular polygon or an irregular polygon, which involves a complex structure where the equivalent area is being developed. So these equations provided by the standard can easily get to that data that is required to determine AD. And based on that, we also have the calculation methods based on the tolerable lightning frequency, NC, events per year. Basically, a simplified risk assessment calculates the tolerable lightning frequency, which is the NC, and compares it to the annual threat of the occurrence, which is ND, which is provided from those maps. So basically, N sub C is a measure of the risk of the damage to the structure that includes the factors affecting the risks to the structure, to the contents, and also from the environmental loss. And it is backed up by several coefficients that you see, which is the C2, C3, C4, and C5, which is all based on the actual structure of the equipment and the contents percent, and also the consequence of getting a lightning strike on it. For example, C2 is the construction coefficient based on the structure, such as a metallic or a non-metallic combustible structure and its corresponding roof, basically. And the values depend on the type of the roof, because if the roof could be metallic or non-metallic, the coefficient's value change to determine the number of tolerable lightning frequencies. Now, once we determine the previous examination of calculating the NC and ND, we have a clear flow of experiment on how to perform the surge protection to be installed on that particular system. So it has been broken down in IEC 62305 on how the step-by-step procedure is performed using this particular flowchart. So to begin with, we start the structure that we are going to identify that needs to be protected, and we identify the types of loss relevant to the structure, which includes the coefficients that I just explained. And then for each type of loss, we identify and calculate the risk components. The risk components that are mentioned in here are basically available in Table 6 or Section 4.2.2 from the standard. One good example is RA, for instance, is considered to be associated with the risk of injuries or death caused by the structure, such as a touch and step potential that is available between the structure dimension or the outer structure and to the actual human personnel. So all these coefficients put together, they do have a proper comparison against the value of the total R, which is the sum of all these risk components. And if it is greater than the tolerable risk component, then obviously a protection is needed. So this is where the assessment starts, whether the risk components added up together based on several factors and several damages decide whether a structure requires an actual protection or not. And each structure is going to be different, and each environmental factor could be different corresponding, and on top of the actual egress of personnel and amount of people inside a structure can cause a different results. So that brings up to a tool that comes from ETAP to provide a solution on how we can perform this for every single structure or a particular equipment building that needs to be protected based on lightning strikes. So if the total risk component is greater than the tolerable ones, if it is yes, then yes, you do need a protection for surge protection. But on the other hand, if it's not, it's optional. That's what the 780 mentions about. And then the next thing is, okay, now that if we need the protection for the lightning, is the lightning protection system installed? Well, if it is yes, are the surge protective devices installed? If it is yes, make sure install other protection measures to make sure that the structure and the associated environments, such as environmental factors such as trees and other power lines or telecom lines that are associated with the structure that are linked to it, or even buried lines and buried telephone lines could have an impact on this lightning structure. Because as you notice, when the equivalent area is calculated, it is spread among the entire building and its associated devices and associated transmission and other power lines or even auxiliary structures that are associated with the main structure. However, if the surge protection mechanism is not installed, what are the other measures that we are going to do? We are going to add more SPM to it. And in other words, we do have the LPS is installed, but still we do have a requirement to have surge protection or not. It depends on the risk components. For instance, here we do have the RA, which I mentioned that it is associated with the risk of injuries or death caused by the strikes to a structure, such as touch and step potentials, whereas RB is the associated with risk of physical damage to a structure due to a direct strike of the lightning on the structure itself. And RU sub A is another important risk component, which is again pertaining to the actual application of the structure. which is the related to injury to living beings caused by electric shock due to touch voltage inside the structure. So here RU sub A refers to the agricultural properties, and RV is component related to physical damage such as fire or explosion triggered by the dangerous sparking between the external installation and metallic parts, generally at the entrance point of the line to the structure. So these coefficients add up to make a decision whether, if it is greater than the tolerable risk components, then yes. If it is greater than that, we need another adequate type of lightning protection system. If not, we could have an adequate surge protection mechanism or SPM installed in it. And this goes on a loop until we establish that we need to calculate new risk values of risk components depending upon the changes to the structure itself or other risk components and the amount of people inside a particular building. So finally, after all these discussions, we can make sure that if we know the correct type of structure and the corresponding types of loss relevant to that structure and each risk components associated with that particular facility or a building, we are able to evaluate whether a risk is involved or a lightning risk is present or not. And by doing so, we can provide correct measures to install the corresponding LPS and reduce and probably mitigate a lot of failures and a lot of flash events that has been happening over the years. Let's switch to ETAP to demonstrate the lightning risk assessment with the available tools and the interface that could be useful to work with complex structures and predefined shapes and the correct method and the standard and the corresponding regional settings. I would like to start with a simple structure here that is a school building that looks more linear. So we have a main structure and an associated adjacent structure. So an actual three-dimensional view, when it gets changed to the top view, we get the actual shape of the building from the top view of that particular building before the lightning strikes. Let's switch to ETAP, and the tool for the LRA is available in the calculator on the main toolbar. And upon clicking it, you get that interface to draw the plan of that particular structure that we just discussed about. So let's start with the main structure. Let's consider that the structure material is metallic and the roof type is metallic. Depending upon the corresponding structure material type and the roof, the corresponding coefficients that we discussed to calculate the lightning flash density for that particular facility would be available automatically based on the standards. So the main structure, let's start with a simple rectangle, and I can be able to use the grid to complete the structure with its corresponding height. So let's continue with 90 feet. And then obviously once we finish this one, we have the ability to add the adjacent structure, which is actually right next to it, but in a much more smaller size compared to the main one. But it is long enough though, but it is still not big enough in that particular case. So if we go to this part and complete the structure, and let's say we put it as 80 feet, so far, we got two structures created, each of them with a different height and the corresponding reference points. And based on the calculations compared to the lightning flash density NG from that corresponding frequency map that we have, and the equivalent collection area that is for this particular geometry, according to the evaluation results, we could be able to infer that a lightning protection system is optional. Now, if you take a look at it, the occupancy egress says unoccupied. Basically, there is no people in this structure as of now. But if I change this to occupied, obviously, depending upon the new coefficients and the new risk collections, right, that would basically change the the recommended setting that you do need a lightning protection system be installed. That changes the whole story of it. Now let's go with the third adjacent structure, and we are able to easily identify the third part of the structure is fairly bigger, and we have the ability to close it out in this fashion. And upon closing it, we specify the height again, and which could be same as the structure number 2, and the structure has now completed for that school building, and the overall results for the evaluation is given to you based on the NFPA 782/2020 to make sure that a lightning system being installed on this particular facility. The good thing about this particular feature is you have the interaction with the map, but at the same time you have the ability to choose the corresponding units, English or metric, and the corresponding standard for NFPA 780/2020 or the IEC 62305. To make the system more accurate, there are a lot of formatting tools for the structure shape and the drawing areas and the plot options per se. And you can also have the ability to delete a structure or add more structures to it. So let's say if we have any transmission lines or basically telephone lines or a power line that is buried or aerial, we could have that added as well. Like for example, if I choose to have a power line aerial, I have an actual structure that could be added based on this particular condition here. So the power line could enter from here and go to this particular case and then reach to this particular termination of that service drop, and then we could be able to close it, and then we can say, okay, this one is also at 80 feet on the top of it. So obviously this power line will also be included on that equivalent collection area, and then finally gives us the results based on whether the protection is required or not. The next example is a complex structure, and it is one of the most popular building in the world. I choose the US Capitol for the second structure, which could have a much more dimensions of complexity. So we have the basic building followed by the rotunda structure, which is 96 feet in diameter and 180 feet tall, which is made out of sandstone and marble. And we do have the dome, which is overall with the Statue of Freedom is 287 feet high. However, the dome is made out of cast iron, whereas the Statue of Freedom, at least 19.5 feet, is made out of bronze. So this could still be created in the lightning risk calculator by getting the plan view of this particular structure. First of all, once we determine the irregular shape of the plan view and the complexity that this building involves, we first identify the location basically. So the location of this one could be brought into the calculator, which is actually in somewhere in the Washington, D.C. area of 8 flashes. The first structure is the non-metallic structure roof and the material type, which is the main one, which is the level 0. We could add that here real quick using our freehand structure, and that would be basically completed based on the actual design of the base. So let's say we assume this one has 100 feet, for example. And then we have the second structure, which is the rotunda, which is 96 feet in diameter and obviously 180 feet tall. And this could be a circular position, which could be hard to do with an actual freehand drawing. So that's why ETAP has some specific predefined shapes that is used in common. And we can add that in here and select the corresponding round. The radius of the rotunda is 48 feet. The height of the rotunda is 180 feet. And the corresponding coordinates can be automatically defined according to the location that is fitting to the plan view of the structure. So if I enter that, I would be able to see the structure being added correctly to the location of it. So the next comes the 287 feet tall dome, which is actually made out of cast iron, and that could be selected as the roof as the cast iron here, and then basically the metallic type to get the correct structure coefficients. And then if we add into it we are able to complete that particular structure with the same length and adding it to the corresponding location here. So this would be 287 feet, which would be the overall capital with the dome, and that would be added up to this particular on top of the rotunda. And then we have the bronze, which is the bronze medal, which is basically the Statue of Freedom, which is 19.5 feet. We could add that as a particular structure on top of this, which could be, in this case, probably 10 feet in length. And adding it to that particular case will give me almost 20 feet of height. And we could add it to a different y coordinate, which is going to be your corresponding selection of that particular statue. So if the lightning strikes in this location, there would be a different assessment compared to the way the strokes on this particular case. But obviously, according to the number of flashes that we have and the equivalent collection area for this complex structure, the lightning risk evaluation does give you that it is recommended that a lightning protection system be installed. So, as a conclusion, ETAP lightning risk assessment tool is capable to have an interface that can handle complex structures, edit different layers, import regional databases, and overall do risk assessment based on the available standards for lightning risk assessment to ensure safety. Thank you very much for attending this session.